So this is for depth filtration just now. So the particles are entrapped over entire depth of filter medium, wide size range, which is for this process it has a wide size range between a 0.1 micrometer for microorganism to 0.1 millimeter. This includes dust and fine powder, and the function of it is probability of particles to be effective range of retaining surface. Removal process is represented by the first order expression, that is the concentration over this is the depth of the filter, is equals to minus K, which is the collection efficiency, and C is concentration of particles in stream. So delta C is the difference in concentration that pass through a certain length or certain depth of the filter, if you remember here. So there's a feed stream passing through the fibrous materials or media of the filter, and the concentration will be different because initially it will have a lot of soluble solid, and at the end the filtrate will be slightly different, will have a different concentration after it passes through the filter media. So that is the delta C against over the distance that it's traveled through the filter media, and you can get this collection efficiency times with the initial concentration. So if you integrate the first order, then we will get ln C over C naught, which is the initial concentration or against the final concentration, or inlet and outlet concentration, equals to minus K times with Z, which is the total depth of filter media, collection efficiency K. K depends on size of retained particles, the filter fibers that are thickness and include the thickness and nature of the fibers, filter porosity, as well as the flow rate that of the fluid coming through the filter media. So K is higher when particles are large, fibers are fine, filter is less porous or dense, which is it makes the filter dense, and the flow rate taking place for example, two scenarios. So if we have a longer retention time, then more absorption, and if you have a higher velocity, it will give a higher impact, right? So this is what this makes the K or collection efficiency higher or more efficient to collect the particles. For surface or barrier filtration, first type is depth N and the second type is cross flow. Depth N, also known as frontal filtration or cape filtration, is when we have a flow direction normal to the filter surface. So we have, this is the flow direction, for example, and you have your media, your filter media here. And what happened is the particles will be retained on the surface of the filter media. The particles are stored and accumulated as cake. Whereas for cross flow, it is a tangential filtration. The flow direction is parallel to filter surface, and the particles are carried forward by flowing suspensions because of the flow is parallel to the surface of the filter. To measure the efficiency of this filtration, we do have the concept of rate of filtration. So what is the rate of filtration measures? It's measure the filtrate volume obtained per unit time. Physically, depth and filtration is flow through porous media. So basic law governing these types of depth and filtration is Darcy law. What Darcy's law states is Q, which is the filtrate flow rate, is equals to dV over dt. So this is the filtrate volume and changes against time. So dV dt equals to the filter area times with the pressure drop across that porous bed or porous filter and over the viscosity of fluid times the resistance of bed to flow, because by time the cake will build up at the surface of the filter, hence create a resistance for the flow to pass through. And this will affect in terms of efficiency of the filtration when the cake is thick. Cake resistance or cake filtration. So the total resistance is the sum of two resistances in series. Resistance of filter medium, RF, and the cake resistance, RC. So R is equals to RF plus RC. This is simply this is resistance created by the cake, and you have the initial resistance of the filter RF. Cake resistance can be assumed to be proportional to its thickness, L. So this is the initial bits here. And resistance of filter medium fictiously at the cake thickness, LF. Proportionality constants R, or m to the power of minus 2, is equals to specific cake resistance. Here, then, the equation of Darcy's law become Q is equals to dV over dt is equals to A times the pressure drop, so denominator is the same. So this is the mu of viscosity times with R, the proportionality constant, times with L plus LF. That is, this is the resistance that we assume it equals to the thickness L of the filter. So in batch filtration, L increases with volume. Two ways. First one, constant rate. We have a constant rate. And the second one is the constant pressure drop. So if you have constant rate, Q is equals to dV dt, constant, and this makes the pressure drop increases so that it can overcome the resistance built up. And for constant pressure, the rate will be decreasing because of the resistance built up. Right? So if here we're going to have a cake, so we need an extra pressure so that the particles can pass through this filter, because the this cake build up at the surface of this filter. So if you don't have that extra force, then the rate of the fluid feed passing through the filter will be decreasing here. Okay, so this is the example of how this constant pressure plot taking place. So this is with the constant rate. See, this is the equation just now, where it is rearranged to get this in this form. So you can see here where you're going to need the Q down here, and this is for constant pressure. So this is delta T over delta V, which is volume against volume. So here you can see here, this is delta P, pressure against volume. Alright. Solution for constant pressure filtration gives the quadratic equation in V. Okay. If you're going to calculate T, then you're going to use V squared times RMV over 2A squared, and you have a pressure drop. So filtrate volume increments delta V corresponding to filtration time intervals delta T are measured based on that, and the ratios of delta T over delta V are calculated and plotted against cumulative filtrate volume V. So this is the cumulative filtrate volume V, and from the slope 2 over C and the intercept 2VF over C, R and VF are calculated. So and it will give you Routh coefficient C, 2A squared delta V delta P R mu times Routh V. Here, the small v. And calculate it. Examples of filtration equipment. Just now we've already looked into rotary vacuum filter. We have sandbed filtration. So sandbed filtration is an example of depth filtration. And we have filter press. We have rotary vacuum filter with auxiliary drum.